we went through a bunch of things, all of them legal, all of them getting a little bit more and more confusing, and eventually we have shown the determinant is a sum of over all periodic orbits. Now how is this going to work? For example, we know in binary dynamics there are only two periodic, there are only two symbols, so there isn't much to count really. So let me just show you how this works in binary symbolic dynamics. Example, full binary. Now, how do we count the case where we know the answer, which was a logarithm of 2, from this totally mysterious and magical formula? Well, we first list the cycles. So what are the prime cycles? There's a prime cycle in which I have 0 repeated for ever, then 1 repeated forever, then 0, 1 repeated forever, then 0, 1, 1 repeated forever. Then we have 0, 0, 1 repeated forever. Then we have three prime cycles of length 4, 0, 0, 1, 1, 0, 0, 0, 1. And if you thought that there is also 0, 1, 0, 1, you're wrong, because that's 2 cycles squared. So that's not a prime cycle. And so on. Then you say, oh, that's very simple. You know, the root is just every time I have a prime cycle. So the root would be always at 1, infinite, repeated. Totally wrong, because this is an infinite product, and you have to be very careful to make sense of infinite product. One way to make sense of it is to multiply it out. So what it is it's 1 minus t0, 1 minus t1, 1 minus t01, just writing what you have there, 1 minus weight of the sec, 2 cycle, 1 minus weight of the 3 cycle, 4 cycles, etc. Now I start multiplying it out, so there's always a term that's 1. Then there's a term which is of order z, so if I explicitly write tp and z to the np tp, I pull out the generating functional weight out. Then I have 0, t0 plus t1, and there's a minus sign. Then at the cycle length 2, I have this guy, so I have z squared t01. Then I have product of these two guys, minus t0, t1. And you keep expanding this, so you know there's a t001, and there is a product t01, t01, and so on. Now, for cycle counting, this is 1 and this is 1, this is 1 and this is 1, and this is 2. So you get 1 minus 2z. This is precisely what we computed before. This totally mysterious formula, if you think a little bit about analyticity and how to represent it, has to be represented as a series in Z, and we know from the left-hand side that for sufficiently small z it's convergent sum. We know how it works. It's determinant. We will now find a finite. So 1 over z, zeta z binary, is simply this very simple answer, even though the formula looks infinite. And this is what happened before in the formula I didn't derive, when I told you non-self-crossing. Whenever you have a self-crossing, you have a situation like this, because you have a cycle that goes from here to here, but then you also have minus product of these things. And if you remember, this is actually self-crossing. We have converted the simple procedure of counting trajectories by their symbolic dynamics. So we give them symbolic dynamics, and we just count how many distinct trajectories are as the time grows. we know that this grows exponentially with time. For that reason, we take a logarithm of that and we define a rate, which is logarithm divided by n, or the topological entropy in this case. And now we have shown you that given the dynamics now, at this instant in time, so what transition matrices tell you, where can I get to in the shortest time step, which in this case is unity for discrete time dynamics, we have propelled you from this infinitesimal or short time dynamics and enabled you to compute an average at infinite time. And this is the paradigm that will enable us to do everything that follows in this course. It's this duality formulas. You can think of it as a kind of generalized Fourier transforms. You have a short time information. If you take a Fourier transform of that information, controls, let's say, long times, or you don't see really the dual variable very well, but the z is somehow dual variable to the time. And if you're interested in long time, we're interested in small values of z. And we can actually go from one to the other.